Alright, now that we have our tools in place, let's see how we can plot the curves and the orbits of some of the other functions which we had only seen as numbers earlier. The first thing we can do is the cosine one. Right? So this will start from minus 1.2 to 1.2, 1.2. Cos x start from minus 7, which is a little more than minus pi. Stop at plus pi, a little more than plus pi. Let's plot the thing of any random number, 50 iterations. You can see that once we do this, it reaches this point, 0.739 whatever. And this is the point at which the y equal to x line intersects the cosine curve. Right. You can increase this a little bit. Let's just make it 14. Let's make it 20. Let's just see, the wave a little bit. See. Oh, sorry. I mean, this thing is only that. So, 20. One of the limitations of the thing is you have to scale x and y equally. So this is something which I've been meaning to fix, but I have no motivation to do it. So this is the curve, but you can't see it more clearly anymore. Right. So this we can see the 0.739 thing, which we had earlier seen in just as a what do you call it? Did you mention it? Yeah, this thing 0.739 is a fixed point for cos. Right. Let's check out some more functions. Let's take the function so let's take the function f of x equal to x squared plus x plus 4. Right? So let's take this one, x squared plus x plus 4. Right? And this function we'll plot it from minus 5, maybe it should be like plus 5. And we'll start from, we'll keep the whole graph also fixed within that much, that we don't need to waste the space, and we can see how this thing works. So, alright, this has two fixed points. One is minus 2, which you can see that minus 2 plus 2 see it is minus 2. Let's see it. Second. Plus x minus 4, I'm sorry. So plus x minus 4. So if we had minus 2, minus 4. Minus 2 is a fixed point. It stays there. So minus 2 is a fixed point. Right? It doesn't change. Similarly, plus 2 is also a fixed point. It doesn't change. Right? However, if you make it, you make this 2.1, it goes off to infinity. You can see it very quickly goes off to infinity, and the program crashes within just 1, 2, 3, 4, 5, 6 iterations. Right? So that's so 2 is a repelling fixed point. Because 2 is fine if you go slightly above. That's the current. 1.9, if you go there, it comes down and goes out of control here. So 2, 3, 4, 5, 6, 7, 8 iterations. So it's just 7 iterations. You can stop. You can see what happens. It comes down from here, it goes here, it comes down, and goes this way, goes this way, goes this way, shoots up here. It's gone. It's a repelling fixed point. What about the other one, minus 2? Minus 2 we already saw. So let's say minus 2, 2.1. Sometimes. So you can see that this is repelling too. It comes out from here, goes down here, goes here, goes here, goes here, goes here, comes down here, goes here, and shoots off. So it's repelling. If you go slightly above, what if you go slightly below? Perhaps that will be some kind of thing. Nope. If you go slightly below, it goes this way and then goes up, comes down, goes up, and shoots down. So we have two roots for this function, -2 and +2, right? We'll just say two fixed points, -2 and +2, both of which are repelling, right? Which is the way this function works. Now let's see the other thing which we talked about. We mentioned another function over here which was x squared minus half. Let's try playing with that a little bit. X squared minus half, minus 0.5, 1 by 2. This I mentioned, it has two roots, one minus square root of 3 by 2 and one plus square root of 3 by 2. So let's just evaluate those. 1 plus square root of 3 divided by 2 square root of 3 divided by 2, and 1 minus square root of 3 divided by 2, and plus of this, but minus on the outsides that we have. So in this case, these two are fixed points. And let's verify that first. Sorry. Yeah. We'll plot it from -5 to 5. That should be fine. Function is x squared minus half. Start is -5. Stop is 5. That is good. We'll take this point, this, put it here, 7 iterations. See what happens. It stays there. Yeah. This is not off center. This doesn't have a zero degree term, a constant term. Because of that, it's symmetrical with respect to the y-axis. Right, so this is a stable point. If I were to increase this just a little bit, go here and make this 5, let's see what happens then. Oops. It seems to be increasing. It seems to be changing a little bit. Let's increase the number of iterations. Yep, it's gone to infinity. I changed it like this much. This was the change. You can see how little I changed it, but within a few iterations, it got out of control. So that's so much for that being repelling fixed point. What if I decrease it a little bit? Just a little bit. Just make this 3. Or leave that as 4. Let's make this thing 5. It's the smallest thing we can do. This, it doesn't change. It's not enough. 3, 7, 8. Yeah, let's just change this. 3. It seems to be reducing. Let's make it increase the number of iterations. See what happens. Yep, it's gone. It's come down from there. It's gone like this. It's gone like this. It's gone like this, and it's come here. Actually, if you want to actually see this, instead of making it -5, 5, we make it 2, because it's 1 point, and it was 1.3 something. So we'll be able to see it much better if we reduce the size of the thing. We'll just stop plotting from this to that should be enough. Right. We'll start from here, 50 iterations. You can see how it comes over here, this way, this way, this way, this way, and finally just comes back and stops at this, the other fixed point. Okay. So as I mentioned, the basin of attraction is within this. If it's inside here, it'll reach here. If it's outside, as we already saw, it shoots out. Now you can see that on the other side, with this point, this was the negative side. So if I go here, take all this stuff out. Okay. Now this point it just stays there. But if I were to let's say I increase this just a little bit, and just push it into the thing, so I reduce this to say 6. Not enough, perhaps. 500 iterations. Yep, it's come back. Right. It reached from there to here, and then it came down here and came this way. So anything on this side would actually first come here, then come down and come over here. So within the basin of attraction, it actually reaches back. So this second point, this is -0.3666, is an attracting fixed point. So this I will just mention this for the other function. This was f of x equal to x raised to 2 minus 0.5. And we have two fixed points, which are this. So 1 plus square root of 3 divided by 2 is a repelling fixed point, and the value over here so that you can see it, and this one is and attracting fixed point. Okay. With the basin of attraction being this minus of this. That's the behavior of this function. Now, we already saw for cosine. We had another function which we played with that had a lot of interesting behavior. Remember what it was? That was our logistic function. We should be able to plot this over here. Let's see what we can do with this one. So, logistic function, let's plot it from minus 5 to 5. And this should be enough. We'll see what we have to do. And let's take what we tried first with 0.5. So let's take 0.5 into x into 1 minus x. Right. We'll start at 0.9. Oh, sorry. We'll start at minus 5. We'll start at 5. And the seed will be 0.9. Final iterations. It's 120 iterations. So in this case, it's going down. It's just 200 iterations. It's becoming really, really small. I think we need to draw this much. So let's just reduce this 3x. So you can see how this, you can reduce it some more. And this is necessary. So you can see how it comes over here, and it comes down over here, and it's attracting this. And these numbers, they e raised to minus 62 and all that, is 0 for all practical purposes. It's not a particularly interesting curve. Let's see what we can do when we change this to 0.8 is also 0.1. I mean, just setting it to 1. Let's see what happens here now. For values like 0.9. Okay, so we don't really need any of this. We just need it's going to be between 1 and 1, because the values have to be there. So we just plot between that. So here. Comes from here, and it's getting there very slowly, but you know, the resolution is not enough, you can't really see it. Maybe increase this a little bit. Even then, I don't think we will see it much. But and also this is not the interesting thing. It reaches 0, but very slowly. Let's look at these. 1.5 tends to 1.3, 1.5 into this. So you can see how it comes from here, goes this way, and comes here, and it converges here, where these things intersect. Right? 0.333, that's like 1/3 of the way between 0 and 1. You can see it somewhere over here. Yeah. So that's with 1.5. Now with 2, it's supposed to tend to half. Right? Let's see if that happens. With 2, comes here. Yep, it actually comes there. It tends to half over here. Right? Curve is shifted a little bit, so now it's gone this way. What about with, what is the other thing we tried? With 3. With 3, it comes there to 2 by 3, but it's a lot more slower, and it oscillates around that point. Maybe we'll just increase this a little bit so that we can see it. 1024x 768. You can see how it's oscillating around that point and finally converging towards it. Like, this is the advantage of graphical analysis, especially if you're doing it with something. I've got just a few 2000 iterations which you get now. So you can see how it goes, how it's going around that point. This going around thing, it looked different when we plotted the linear plot. This was the line, and we could see these 2 points on both sides over here, but seeing it go around like this is more interesting. So it's converging at that point. It's sort of narrow, zoning in over there, but it's taking a lot of time, and it's oscillating around it left and right. So this gives us a much more clearer visualization of what's happening. All right, what is the next one? Period 2 cycle. We have never seen these before, so let's try that. Period 2 cycle should happen with this equal to 3.2. Let's try that. So you can see it flashing over there, and it's over here and over here. Right? This is a period 2 cycle. There's 2 points on the curve where this thing is touching. This is a period 2 cycle. What do we try next? Let's try the 3.5, which is period 4 cycle. Now the astute among you will have noticed that it goes from 2 to 4 to 8, and it sort of bifurcates. This is this thing called how to predict these things called bifurcation theory, which we'll discuss in one of the later segments. Right, let's see what happens with a period 4 cycle. Oh, so now we have a period 4 cycle. There's one over here, right? There's one over here, and there's 2 over here. There's one over here, and there's one over here. So you can see the ones that are flashing the most. It's sort of, that's the way you can see this. And I suppose you could, change the coloring and the scheme a little bit to show it a little bit more clearly. But this is, you can see it happen. Finally, we'll try 3.55, which should give us a period 8 cycle. It should be even more interesting. So now we have 2 over here. I think there's 1 over here, 1 over here, and then we have 1 over here. So 2 over here, 1 over here, 1 over here, or something. Right. So now we have a period 8 cycle. It stays there. It doesn't plot anything else. That's the point. Okay. Now we can go further, and we can see what happens when we mess with this a little bit more. Let me see. There is one which we didn't talk about, which is 3.83, which gives us actually a period 3 cycle. Right. You see that? So this actually, let's just see. Yeah, so there's 1 point here, there's 1 point here, and there's 1 point here. So the points on the curve where this thing touches, there's 1 here, you can see it. Nothing over here, there's 1 here. Come down here, there's 1 here. So this is actually a period 3 cycle. Right? So this is a period 3 cycle with 3.83. Finally, we had 1 when we reached 4, because it would be absolutely chaotic. But it would stay between 0 and 1. It wouldn't go out of control, in the sense it wouldn't go to infinity or anything, but it would be completely unpredictable. You can see what happens. It just fills it up. There's no periods, there's no points. It hits it at random. It's almost random. It just fills up the entire part. And this is by changing ecological constant by such a small amount. You can see how it fills it up. If even once the number repeated, then from that point onwards you would get back the cycle again. But it never ever does, which is absolutely amazing. So you can't really see any more patterns in it, but it just fills it up completely. Okay, so let's close that. Finally, if we go slightly above this, we can see how things just blow up to infinity. Boom. It went out and went down here. So it's already gone up to this. If we increase the number of iterations, so we could, let's say, 2,000, make it 3,000. Let's 300, sorry. 3,000. Yeah. And you can see how the numbers start growing. Alright, so this is the way the logistic function works. So I showed you. Now, so you can use this tool to visualize various kinds of curves and how they behave and all of that. So with this, I think we've come to the end of this series of screencasts about basics of nonlinear functions and how to plot them and see what you're interested in. I have some notes in some of the videos about the textbook which I've used for this. If you're interested, the textbook is called, let's mention it over here. The book which I've used for this is called Chaos, Fractals, and Dynamics by Robert Devani. This is a textbook which I've used for this. So, thank you for watching. Feedback is welcome.